So this is Valentin's second lecture. We'll continue, and I think this time he has remembered to share his screen.
Yeah, it's sometimes difficult to remember all the things like the recording on Zoom and at the same time sharing the screen. So welcome back. We're again shifting gear and going from atomic physics to semiconductor physics. And let me just remind you of the key things that I went over last time, which was basically an introduction to semiconductor physics. And so there are basically three key takeaway messages that I want you to remember. The first of which is that light induces vertical transitions across band gaps. So here from the valence to the conduction band. Okay. And so we described these bands like in K.P theory, and then evaluated this optical transition. And so this is basically the first takeaway message, that there are these vertical transitions. Now these vertical transitions allow us to understand excitons basically. So we saw that they're below the band gap. There are these excitonic states, and today we'll see much more examples of that. And how we can formulate excitons. And it turned out that an excitonic state is basically the state. It just consists of vertical band transitions of an electron and a hole with this relative wave function alpha k. And so then I showed you that this wave function can actually be described in a real space representation. And so we get basically a Schrödinger-like equation with the center of mass with the relative coordinate and a potential that binds the electron and the hole together. And so separating off the center of mass, this leads to a so-called Wannier equation, which is this one here, that we'll look at in more detail today. Okay, so then we learned that Wannier excitons are bound electron hole pairs with a free center of mass motion, and they have a series of excited states that we'll look at today. All right, and so finally we looked at the properties of Rydberg states. So how do, or like of excitonic states, so how do we excite them? What's the matrix element? And it actually turned out that the matrix element to excite excitons is proportional to the relative wave function here, alpha nu of r at the origin. Whoops, so actually I just realized this is a 0 here. So the origin of the relative wave function. Okay. So this is where I'll continue now, and I will just make two more basically remarks about the physics of Rydberg excitons, and then we'll go like into some more recent developments and where I see like where this field is moving and what prospects are. Okay, so the first comment is that excitons can exist in various dimensions. And in particular in lower dimensions. And so here we'll start with just with the Wannier equation that I showed you before. So that's the kinetic energy of the relative part. Then there's this potential. Sometimes I leave out this label here, EH, so the electron-hole interaction. And so there are many states, the Rydberg states, alpha nu. Alpha nu of R. And so like to understand kind of how excitons are different from atoms, we'll now use a very simple approach. And look at this potential, which typically is the Coulomb potential. So in the simplest case, that's the Coulomb potential. So it's minus E squared because the charge of an electron to hole is the electronic charge. And then 4 pi epsilon 0, that's what you know from all of atomic, or like from the hydrogen atom. but there's this factor, the epsilon r, the dielectric constant of the semiconductor, that basically weakens the attraction. Okay, so and at this level, we can already make some kind of interesting conclusions. And so to see this, let me introduce dimensionless parameters. So we somehow scale all length scales r by some arbitrary unit r0, and we introduce and we scale the energy, all energies, by an energy unit E0. And so when you just like, this is like how you would always like kind of make any differential equation dimensionless. I just showed here for like to illustrate this point. So then you get the minus, like the R0 squared from the spatial derivative. You also get the, and I divide everything by the energy. So now we're taking the derivative with respect to that scaled variable. And so so now for concreteness, I put in the Coulomb potential with the dielectric screening. So here again, there's R naught from this 1 over R factor and an E naught. So it ends up looking like this. So that's a mu, so that looks like a 0. E nu alpha nu R. Okay, and so like always in scaling, like when making equations dimensionless, we can now take certain parts of the equation, let's say this part, and we also take this part. And because we have two independent variables, so we have the spatial variable and like an energy variable, we can demand that they both be 1. So now, if that's the case, right, the equation looks much more simple. And so by demanding this, you get you get an expression for like the optimal, basically the optimal choice of these of the length scale and of the energy scale. So you find that the length scale looks like this, and the energy scale, oops, that's e to the 4. Looks like this. So that's already kind of an important conclusion, and you will see a little later why. Okay. So now what we're left with is a scale invariant, or like a dimensionless equation that looks really simple. So you just have a kinetic energy term. What remains of the Coulomb potential. So that's the scaled equation. And now, so you see that this equation already, that looks like that is just a hydrogen equation in its simplest form. And so now, like looking at different dimensions, so I will not go through the solution, but if you're interested in that, you can find it in most textbooks on semiconductor physics. So of course, like in atomic physics, it's usually this equation is solved in 3D for a 3D electron. But in semiconductors, there can be two-dimensional structures, and then maybe you want to solve this equation in 2 dimensions. So the strategy of doing that, or like getting there, is, of course, in 3D, you can separate into a radial part and then into spherical harmonics. So that would be in 3D, but in 2D, you can do a similar trick, and you can just separate off these exponential factors. So the physics actually of 2D hydrogen is kind of interesting. So because this allows it's just on the boundary of having a lowest bound state, but actually the system, I mean, the system does have a bound state. So let me. It's told to scroll up sometimes so that you can see the last equation. So like the quantum numbers in 2D and 3D. So in 3D, of course, we have quantum numbers n, l, m, so without spin at this point, where L needs to be smaller than n minus 1, and m can be anywhere between minus L and L. In 2D, now you just have two quantum numbers, you just have n and m. And so the n quantum number can go from minus n plus 1 to n minus 1. And so when we talk about Woodberg states, of course, a very important property is how the energy scale and how the separation, like the size of the wave function scales. And so in 3D, we know that the energy En, so you can just calculate that from this Wannier equation. So you get E0 divided by 2n squared. And so here you already recognize that this is something that you would call, that's often called the Woodberg constant. But that is the Woodberg constant. And in 2D, actually, this formula is almost the same, except that it's E0 divided by 2n minus 1/2 squared. So because in both of these cases, n starts at 1 and then continues just over the integer numbers, we already see that the ground state energy of 2D hydrogen is actually 4 times larger than it is in 3D hydrogen. Okay, so and at the same time, like kind of what I said is also important, the expectation value of the radial coordinates. So I think this is so this is like some that goes as 3/2 n squared in 3D and also in 2D. So you see like kind of the Woodberg physics of the large, like gradually growing size of the Woodberg radius. This is true in 2D and in 2D. Okay, so since we'll later also see 2D excitons, I'll just write this down. This comparison, so excitons in 2D have larger binding energy, a smaller Bohr radius. This is due to the larger attraction, so it's smaller. But the same Woodberg scaling. All right. So that was comment 1. Let me continue with comment 2. And please again interrupt me at any point if you have questions. And so the third point is a comparison with atoms. So now we have this very simple model where there's just like, it looks like hydrogen, except there's a screening and there's a reduced mass. So these are, so the new components, or the, so we really have to look at epsilon r and mu. So mu was, just to remind you, was the mass, the product of the masses of the electron and hole divided by their sum. And so if we now look at these scales that we have introduced here, so E0 and R0, we can relate them quite easily to atomic cases, or like to the atomic system. So E0, I can write this by the reduced mass that I introduced, divided by epsilon r times the mass of an electron. So I just extract some factors. And what's left is E0 atomic. I can do the same thing for R0. So R0 is epsilon r times the mass of an, okay. So sorry, this should be mass 0. So this is the electron mass in free space. M0 divided by mu. And that's the Bohr radius of an atom. Okay, so you see that like these fundamental energy and length scales of atoms are changed in the semiconductor via the screening, the dielectric screening on the one hand, and the reduced mass, or like the different masses of the electron and the hole compared to the very heavy proton, or the nucleus and the electron. So let me give you an example of what that does. So in a material that we'll just look at a little more carefully in just a second, cuprous oxide, mu, the reduced mass, is 0.35 the rest energy of, or the rest mass of an electron in free space, and epsilon r is 7. So when we now look at this, and I just calculate, for example, the binding energy, that would be, you know, like the Woodberg energy basically in hydrogen. Now that is reduced. If you just enter these numbers, we get an estimate that this will be on the order of 100 millielectron volts. So we go from 13.6 electron volts to 100 millielectron volts. So very much more shallowly bound states. And the Bohr radius in an exciton becomes about 20 times the Bohr radius in an atom. And that's like 1 nanometer. And so here, I just want to point out that 1 nanometer, that's much larger than crystal cell. So crystal cell has a size of maybe an angstrom or something, and so we are like on a length scale of a nanometer, so much beyond that. Okay, and so maybe the most important terms, or like the most important point of Woodberg physics, as we just like started seeing in Misha's talk, for example, are interactions. And so now let's compare interactions between Woodberg excitons with interactions between Woodberg atoms. And so I'll just go a little more into detail where this interaction comes from, but this is exactly what we already saw in Tillman's lecture. So the dipole-dipole interaction for faraway particles is this one. So you get a a direct, or like kind of this term, and then there's a second term. So these terms are basically what Tillman showed us, what does like leads to this geometry dependent attraction between dipolar aligned atoms. But here, so that's the vector connecting to excitons. So we kind of have something looks like this. So two particles, and that's their connecting vector. And here this is R1 for the first electron and R2 for the second electron. They can be in any sort of direction. Oops. R3. Okay, so now what does this Rydberg interaction, or like what does this dipole-dipole interaction do? It leads to this, Misha explained, like this C6 over R to the 6 potential. And where does that actually come from? So we can, this is something you can understand in the address state picture, or by something that's analogous to a Stark shift. So basically, in the very simple case, so this is like a cartoon picture now of this dipole-dipole interaction. You could start with some state that's now a state of two atoms, for example, or two excitons, two S states. And so this dipole-dipole interaction induces a transition to some states of P character. Could be PP or PP prime or something. And this state is at an energy, the energy difference here is delta, which is called the Förster defect. In any case, so like to understand like what this interaction now does, so the interaction promotes, maybe I should draw it better like this. It promotes jumps up and down across these two states. And so now, like trying to apply a simple picture, let's use the kind of the Stark shift that we just learned about here. So what does this interaction do? It actually, the asymptotic interaction will be one where so let's make it call this the van der Waals, where the dipole operator acts twice, and then you divide by this Förster defect delta. So that's basically the same, like you can understand that in the stress state picture. So like if you consider this with a dipole-dipole term here. So now if we now look at this Hamiltonian here, like what happens? So you have this, like let's first look at the first term. So there's this R1 and R2, and they both, like in this case, in the simple example, they act on the same state, so they transition to a P state, and there's some energy difference. And so like the scaling here, just to understand like where all of this comes from, is roughly like the expectation value of the radius, basically, right? Like this is what we do here. The expectation value of the radius. But then because there are two particles, it's actually the expectation value of the radius squared. And then because we take the square of the interaction, it's that squared divided by delta. And so in total, you find something that looks like this, like kind of has this Woodberg scaling and then falls off as R to the 6. Because that's kind of like second order perturbation theory. Now, this formula already explains like why in atoms we get this like n to the 11 scaling of the Woodberg interaction. But here, because we're talking about excitons, I will not make that point. I will try to convince you like how we can get from the scaling argument here, how we can now derive a scaling comparison between the interaction of atoms and the interaction of excitons. So now if we look at this, right, so it's like so if I want to calculate V van der Waals of excitons, and I just want to do like a back of the envelope scaling argument, then I see that I have to include all the factors here. So we apply the van der Waals, like the dipole operator twice. So what we pick up is like first, in comparison to atoms, we get a scaling of 1 over epsilon squared. So that just comes directly from the Hamiltonian here. And so the second, or the remaining parts can just be read off this formula here for the dipole interaction. So basically what we have is a length scale that's taken to the 4th power divided by an energy scale. And so what we saw before is how energies and length scale scale. And so if we put all of this together, oops. What you end up with is epsilon r divided by mu m0. So that's just, this is from the 4th order of the length scale that we have. And then from the energy scale, you get a factor epsilon r squared divided by mu m0. And so that's kind of the relation between the excitonic strength of the van der Waals interaction and the atomic strength of the van der Waals interaction, just as a back of the envelope estimate. So now we can simplify this, and it ends up as epsilon r to the 4 divided by mu to the 5 m0 to the 5. So of course it's a dimensionless number. And so the remarkable thing is that if you now compare, or like if you now use the values, for example, for cuprous oxide, so we use this mu equals 0.35 mu naught and epsilon equals 0, epsilon r equals 7, and then you find that this value is about 500,000. So what this means is that we expect the van der Waals interaction, the asymptotic interaction between two excitons, to be about 500,000 times stronger at the same quantum number as you would see it in atoms. And the underlying reason is just that the Bohr radius is much larger, so the particles are much larger and more polarizable, and the energy differences which matter in this 2nd order perturbation of the van der Waals interaction also become smaller. So are there any questions? Okay, you can think a bit more about the questions, because now I will switch to a slide presentation. I hope that works. No, it doesn't. Okay, I don't know how to solve this problem immediately. Well, okay, so I guess you always just ignore the second slide that you already see coming up. And I promise there are not 175 slides. So let me. Wait, actually, that's right. This is how it works. Okay, great. So let's see. All right, are there any questions while I'm setting this up? Anyone who doesn't believe that interactions are 500,000 times stronger? Sure.
Is it really a fair comparison? In a sense that what we do to compare interactions, excitons, the excitons with other types of interactions that exchange interactions, but also wide types of excitons, which are much shorter.
Right.
Right.
So it's not, in that sense, it's not an entirely fair comparison. So you have to really make sure that you get all the other scales of the systems right. I just want to show you that in this very back of the envelope kind of argument, you see that the interactions there are much just the dipole interactions are much stronger. But of course, the exchange interactions are, for example, very relevant at low quantum numbers.
You make a comparison maybe and what you
What's that?
Lifetimes.
Lifetimes. It's not in this part, but I mean, I'll happily talk about the lifetimes and such things later. Okay, so I showed you that the binding energy of an excitonic state is important, and so is the gap energy. And so here, this is just from a textbook. I selected this this figure that really shows you that there's a lot of semiconductors that somehow have a sizable an optical band gap and binding energy somewhere between, so lowest, this is a famous semiconductor here, gallium arsenide, with fairly low binding energy and excitonic binding energy, 4 electrovolts, all the way up to fairly highly bound excitons, and we'll talk now about one specific one that I already mentioned, cuprous oxide, which lies here, and another one that actually lies even further above. This is 2D semiconductor. Okay, so this material, cuprous oxide, looks like, the first experiment that Tillman already, now I'll show you the experiments that Tillman mentioned, was performed on this crystal. But if you really if you isolate the crystal into a nicer form, then you see that it's this nice ruby color here. You really get nice stones. In any case, okay, so what we see, what was the surprise with this crystal? So this crystal actually, historical remark. This material was the first where excitons ever were observed, actually in a group at the Young Institute in St. Petersburg. And then for an anniversary, I don't know, 70 years of something, first excitonic discovery, a group in Dortmund tried to measure the same old series again for sentimental reasons, I guess, but they did this with better equipment. So they now have better cryostats and better lasers. And instead of before, you saw maybe one exciton and a second, maybe the third, and all of a sudden they could resolve an entire zoo of states here. So we see the optical density, so how much light is absorbed from the crystal as a function of the input photon energy. And so then you can zoom into this zoo here at the end, and you really see that it continues and continues and continues, and so you end up with really lots of states, so n equals 25. And so with what I told you before, right, on the simple level, disregarding all sorts of other effects, this n equals 25, this 500,000 increase translates to an increase in the principal quantum number compared to atoms by about 3.5 or something. So it's n to the 11. Scaling, so you can really think about these excitons here, that they're so as strongly interacting via dipole-dipole interactions as atoms in the n equals 100 states. Okay, so now, I mean, this is kind of like, this is the cleanest crystal where excitons or Woodberg excitons ever were observed. And so here, I'll just show you a mind map of different research directions as I perceived, or like kind of as they came to my mind. So this map is not complete. It's not, I mean, it's pretty personal, I guess, like, but this is like my impression of the field. And so like the first years have seen like investigations of the properties of these Woodberg states. So effects of band structure and selection rules that are broken. So the typical selection rules that you find in free space are slightly broken in crystals. There's studies of quantum defects. Then there have been investigations of the electron of the exciton host interaction. So coupling of Woodberg excitons to phonons, for example, screening by residual fast mass, impurity interactions of Woodberg states. There have been groups have looked at the effects of external fields, so calculated Stark maps of excitons. Actually, because of these light masses of the electron as a whole, Woodberg excitons are a nice system to look at quantum chaos. So I guess like that was also mentioned. Apparently, that was a big topic in the 70s and 80s in hydrogen and strong fields. So here, you need just much weaker fields again because the energy separations are weaker. Another kind of neat idea was to look at the interaction of Woodberg excitons with orbital angular momentum light, so really structured light, because if you have a large particle, you could conceive like breaking the typical dipole selection rules, like with this different type of light. A group in St. Petersburg has looked actually based on like our calculations on many body states of ground state excitons. And they found like some topological ground states in linear chains. So this I think is like a little further from experimental realization than the other states, but it's like there's interesting physics there. Here, like in this is a field that I'm very interested in, like nonlinear optics. Like how does Woodberg decay? What that Misha already mentioned, like what is the effect of that on the optical response? And that has been seen in atomic gases, but here, like how can we understand how the nonlinear response of Woodberg excitons due to Woodberg decay? So there's been studies of nonlinear absorption and explaining that theoretically. That's something that I've been very involved in probe spectroscopy. So pumping one exciton species, then probing with another. We're currently working on time-dependent spectroscopy in collaboration with a group in Dortmund. Really like trying to have a time-dependent pulse and seeing how that affects the system. I guess here this is like much more applied, so integrated application. So can we now take this system and can we use it for something? So here, for example, group of Charles Adams has started looking at microwave to optical transduction. So the idea is like, can I somehow convert a microwave photon into an optical photon, which would be a very nice application for all sorts of things, coupling superconducting qubits to waveguides or something like that. Crystals have also been grown. So like kind of instead of taking the bulk crystal, just taking microcrystals of these semiconductors and patterning them. So really like in the sense like providing some sort of quantum dot arrays. And so that's another very, very interesting topic here, cavity polaritons, which I will talk about like just in a few moments. I'll talk more about this. And then there are low-dimensional materials. So, so there's not only carbon oxide, there are also other materials. And like one system that I think is very promising, that these low-dimensional materials that like in the wake of graphene have really risen to prominence. So like transition method like Valentin. Yes. That has been looked at. Oh, I don't know why that disappeared, but yes. So I mean, like people have looked at basically pressing needles onto the semiconductor, which induces strain and thereby like locally traps excitons. So this has been used actually like back in the day for like to look at both Einstein condensation of excitons, where you really want like high densities. I don't know exactly what the current state is, but in principle, that's possible. Yeah. And another way is, of course, like micro fabricating crystals, are really having like patches of crystal here, patch of crystal here. Okay, sorry. So like I'll be talking about these two topics now: like cavity polaritons and monolayered semiconductors. So those will be yeah, the two topics. Let me just check how I'm doing on time. Yeah, 20 minutes or something. 20 minutes or something. Yeah. All right. So so this is like the paradigmatic example of what happens if you can couple light strongly to matter. This is really, I mean, we haven't really talked about this much at this conference yet. Tillman has mentioned it a bit, but like what can happen if you confine any polarizable medium, that could be atoms or here a semiconductor, to light, then you can get various states again of a photon, for example, and an exciton. So you can really, if this coupling is just strong enough, you can really get superpositions of having a photon and having an exciton. And so the condition for that to happen is that the excitation rate or the exchange of energy between the photon and the exciton is larger, so that happens at a faster time scale than both the decay rate of this exciton into some other channels and the decay of the photon through the cavity walls. And so what, like typically it's easy to do that if the dipole moment of the exciton is very large, and therefore naturally already coupled strongly to light. But that's actually not the case for a cuprous oxide. Therefore, it's been like for a long time been very difficult to kind of like push towards this regime here, where you get these light matter coherent superpositions. And so these superpositions between having some matter degree of freedom, in this case the exciton, and having the photon, those are called polaritons. And so this is what we see here in K representation. So this is like kind of this is the photon. So like kind of the photon dispersion in the fabric curve. Imagine you have two mirrors, and basically light is confined in one direction, but it's free to move in the other. So therefore, you get parabola. The thing is that the mass of the exciton is still large on these length scales. So this parabola, this is the parabola. It's just like very, very flat. And so then when the energy of the exciton is resonant with the energy of the photon, then there can be exchange of this excitation from the exciton to the photon, and you get polaritons. So these are the dashed lines here, the blue lines, sorry, the lower polaritons and the upper polaritons. So these are very interesting particles because they combine light and matter, and could, for example, like be used to make photons interact. That kind of what Tillman was talking about, which is kind of like one of the central goals of quantum optics. Right? We want to have strong nonlinearities at the level of ideally few photons. And so now, if we take a cross section here between across like one of these energies at this crossing point, what we see is that the line of the exciton, which normally is just like this Valentin line, really gets split into two different lines. And so you might wonder, like, why is this so asymmetric? And that's like specific to cuprous oxide in this experiment. They actually like I worked quite a bit on like explaining the splitting. So if you're interested, I'll be happy to discuss it. But like the main point is that you really get the splitting. And so, like I said, it's kind of difficult to do this in cuprous oxide, but a group of Hamid Ohadi in St. Andrews just recently managed this. And so the paper is about to be published. So this is preliminary data where these Rydberg exciton polaritons actually are observed. So here you see kind of like multiple bands. So the real cavity height doesn't just have one photon band, there's multiple photon bands. You really see that there's crossing between n equals 3, n equals 4, n equals 5, n equals 6. Not all the way up to n equals 25, but already like a very good start. And so, like I said, like the strong coupling limit is the limit where this G is larger than all the decay rates. And that's not satisfied for all the principal quantum numbers, but it's satisfied for 3, 4, 5, and 6. So here the experiment is above the strong coupling. And I think, like, to me, this is really like a very promising outlook now, that you can couple Woodberg excitons to cavities and thereby have like access to the light degrees of freedom. So now that might be a possibility to use these Woodberg excitons to manipulate light. Are there questions?
Yeah. Sorry, on this slide, I thought I understood why there were 2 peaks, but why is there a third peak in like n equals 6?
Yeah, that's an excellent question. So that's like just from the experiment. Here, like this is splitting at the n equals 6 peak. So that's like kind of the light matter coupling splits it into 2 peaks, lower and upper state polarity. But then actually the adjacent peaks. So here the adjacent resonance n equals 5. That kind of made it into that jump picture. So that's also here. All right, so let me just go to the last point that I want to talk about. I already said like kind of photon-photon interactions are very interesting, and maybe there's a way of inducing them with cavity-coupled Woodberg excitons, for example, in bulk materials. But isn't there also maybe another way that avoids this cavity complication? And so one class of very interesting materials, as I said, these transition methodical carcinoids. They look like this. So you have like there's a layer of transition metal atoms in the center, and there are carcinoid atoms on both sides. So if you look at it from the top, it looks like graphene almost, like this hexagonal structure here. But it's really like it's only like almost only one atom layer thick. And so there's lots of interest in these states, like for correlated electronic states, you can twist them like graphene. There's all sorts of interesting physics happening there. But one property that I will talk about now of these states is that they actually can be almost perfect mirrors. So this was actually shown in Misha's group and in Touching the Woodberg's group. And here you see that it doesn't come out so well. Like that's the paper, the first illustration. So here you see like a kind of a flake of this material on some absorbing background, and so here the illumination is resonant with the excitonic transition, and you get very high reflection. So 85% reflection. I really want to emphasize that that's remarkable. Right? Like kind of if this very thin material and any atom, like if you have just an atom, like a few atoms, like photons will always travel to just past that system. So here you have a system that really, although it's as dilute and as thin, it really reflects light pretty perfectly. And so that this is not an artifact can be shown by removing that resonance somehow. So here it's doped, like you kind of switch on a gating, like you shift the excitonic resonance, and then the same reflection peak that you saw before is gone. So that kind of like gives you this linear property of like having this mirror. But actually, a challenge could be like, how can we now use that to induce photon correlations? And so, like, we're coming back to the topic of the school, Woodberg states. So Woodberg states has been seen, of course, in copper oxide, but also to a lesser extent in other materials, like these two-dimensional materials. So here we see the first experiments with n equals like Woodberg states up to n equals 5. Here, these are more recent experiments going up to n equals 11. But I should say that this has to be taken with a grain of salt. So here, this is the photocurrent measurement, which is a bit indirect. But what I want you to take away from the slide is that there's hope to see like these Woodberg states, and there's really nothing that stands in principle in the way of seeing Woodberg states. And in this case, there would be these two-dimensional basically in the simple picture, two-dimensional hydrogen atoms living in a plane that we discussed just a while ago. So now, if you have, like, let's now put all the ingredients together. So we have like this mirror. We have Rydberg interactions. Let's say, like, just for the argument's sake, the Rydberg interactions are very large. This blockade radius now spans the entire illumination spot. And we already learned about EIT. So here, like, if you don't remember, it's like just here on the slide. So EIT is a technique of making materials transparent. So if we, and it's also very useful in inducing photon correlations. And this EIT, electromagnetically induced transparency, I mean, of course, means that media become transparent. They don't absorb light. So, okay, so I think the first illustration is actually just of a mirror. So if you don't do EIT, you just have like this first laser on, like then, of course, photons will bounce off this mirror. So that's a mirror. But if you have this Rydberg coupling to some state, for example, a Rydberg state, and you send individual photons onto that system, then these individual photons will all see EIT and basically just be transmitted through the material. So this is what we see here, photons just coming and flying through. So now that's maybe not so interesting, but you have to note that although the transmission through this material is perfect, there's a certain time that's associated with the transmission of a single photon through that mirror. So the photon comes, and while it goes through the mirror, it actually, in part, becomes a dress state, becomes the dark state actually here. In which, and at that time span, it acquires like some part of the matter excitation, and then it gets released again and transmitted through the mirror. And you can actually show that the time the photon spends in the mirror is exactly given by gamma over omega squared. So it's controlled time scale. So now, like, kind of what's the naive expectation of this mirror? So if we now send not one photon but many photons onto the system, then we expect that like one kind of goes through the mirror, right? Like it creates an excitation, and while that excitation is there, EIT is broken, and the remaining photons just leave the mirror. So they are reflected. And actually, like in under some assumptions, this the light field that is transmitted, like can be analyzed and can be actually calculated analytically in this case. And so here we look at G2. I think we already looked at G2, like the correlation function of light. Here, in this case, the transmitted light field. And we see like at long time, so at long times tau is this time that it takes to get to the mirror. So at long times compared to that, so this delta tau is the time it takes to go through the mirror. So here there are no correlations. So G2 1 just means that the light, that the incoming light is basically uncorrelated, has the statistics of laser light that we come to system with. But here, like this is like the correlations are really enormous. So you have the probability of having two photons transmitted at the same time with a time delay of 0 is very, very low. And so this is like something that you could call quantified as photons. Okay, so then by driving stronger, you actually like get like some interesting behavior. So this correlation function actually starts oscillating, doing Rabi oscillations that we already talked about, and then like also like this anti-bunching here at small times actually gets a little worse. And so like one last comment from my side is that that of course all of these applications, decay is somehow relevant. So like if you have to, like Woodberg excitons are unstable, and so you somehow have to look at like what's the effect of the decay, and does it preclude the application that we just thought about or cooked up. And so here, like the dominant decay channel is actually the Woodberg state. So if the Woodberg state decays or dephases, like what does that do to this nonlinear mirror application? And so here, so I scaled everything in terms of the units of this lower state decay, which is pretty large. So here the red line is no decay on the Woodberg states. So that would be the perfect line. And then as I increase the Woodberg decay in the model, you see that these Rabi oscillations get damped, and at some point they will decay. But the point here is that this 0 point value, so like the value of the G2 function at 0, that indicates like how anti-bunched the light is, actually isn't very much affected by this. And so like kind of getting correlated photons from excitons is actually something that has been tried for a long time, and it really hasn't been easy to go to much lower values. So actually, there were 2 papers like from 4 years ago now that did this with gallium arsenide, so in a cavity, really like pumping hard, very small interactions, and so there the value of this one, like kind of this perfect, like completely correlated light was just lowered just a little to go to 0.95. That was already like a very, very good result. So I think like this record value, so of course that's a slightly skewed comparison because that's a totally different system, but like using this mirror property in connection with interactions can really be can push towards much lower values of this correlated light with excitons. Okay, so this brings me to the conclusion of my talk and lecture here. So like I think like what semiconductors really do is that they bring strong interactions to the solid state. And I've shown you that excitons are complementary somehow to atomic systems, so they have very different masses, they have different length scales, and importantly, they have very different interactions. And so interestingly, that like the physics of excitons can be connected to strongly interacting polarities, for example, by coupling them to cavity, also by using EIT schemes. And that has applications for fundamental physics. So I didn't talk too much about this, but you could, for example, think about like really getting BECs of excitons that have been around and thought about, or like BECs of excitons or polaritons, and connecting them with strong interactions. And so then the applications are really, I think, are still a bit up in the air. So this, in my view at least, is a field that's just like making the first steps, understanding how the system works, understanding the single particle physics, understanding the two-body physics. But I mean, it's interesting at least to think about potential applications in terms of quantum optics and maybe even simulators or quantum gates maybe down the road, if things like decay, dephasing, and so can be brought under control. And another thing that I think is very interesting is to use these excitons as probes. So Woodberg states, I mean, Jim's lecture, like kind of how atoms, Woodberg atoms, can be used as probes of microwave fields. So why not use excitons as probes of other fields that could, for example, come from the semiconductor itself? But really, as I said, like all of this is very much open for discussion, and everyone is a school here, all experts on Woodberg physics. So I really invite everyone to discuss like similarities, differences, like potential applications, and just like think about the system that also shows Woodberg physics. Thank you for your attention.
So we were wondering about something, say, an axon for a river atom, or even maybe microwaves, or the excitons are involved.
The excitons are in the semiconductor, yes.
How probably low the surface are, how strong the coupling, say, to a microwave waveguide.
So, I mean, okay, so 2 comments maybe. So in bulk crystals, you just like consider them in the bulk. And so they're like the experiments of Charles Adams' group, couple them to microwaves, and these microwaves penetrate the semiconductor. So I guess this is because I always assumed that this is because the semiconductor is transparent to these microwaves, but probably it's not quite. So you would have to see like how far the field actually penetrates and what the absorption length is. In terms of sensing, maybe an alternative would be to use 2-dimensional materials, where the exciton obviously is just like in the material, and so it's like much more sensitive to whatever happens around it. In fact, actually, like has been considerable interest in like the physics of twisted bilayer TMDs where like electronic states, very interesting electronic correlated states appear. And so one of the best ways of measuring what happens in that system is by placing a second layer, or like in principle a third, but you have a bilayer system, and then you place a molar layer of TMDs in the vicinity. And what's measured then is, I think, like the reflection, or like some like a change of the 2p state, 2s state of the exciton in that adjacent semiconductor. So you basically use something close to it as a sensor of like some correlated states in the semiconductor.
So if I think that about the size data, then I should think that this center of the exciton is for higher bands should be further away from the surface. That's the reason.
Again, so the
For
center.
higher values of n, where the radius of the wave function is bigger, then I should think that the exciton must be located deeper below the surface.
Right. So I mean, like kind of that's a very interesting point, right? Like what happens to the exciton when it comes close to the surface? And I think there's old research on this. I think that's still like a bit unclear. So if you like how small can you make a semiconductor before it really starts seeing, before the exciton really starts seeing the surface? That's actually like an important point for these cavity experiments where you want like a kind of a small semiconductor. So you narrow the semiconductor down to a thickness of maybe 30 microns. Now you can go maybe to 20 microns, potentially go even lower. So at some point you get to the length scale, but the semiconductor is as thick as the exciton is large. So then the excitonic state will change. So then you get like size quantization effects, for example. Yeah.
Question.
How should I think through for exciton? I mean, every concept before after, and then where you have core, and then electron far away. But I mean, the exciton doesn't really have.
Well, it has a hole as an electron that are like on the same order, like their masses are on the same order of magnitude, are like kind of comparable. So basically, what you should think about, like, it's not a kind of positronium. It's a kind of positronium. So you don't have like a core and an electron circling it, but you really have like a compound that circles each other, but with the center of mass that still that can move. So it's like it's actually like discussing with Steve, there's really like an intimate connection with positronium. So also like the excitation probability of positronium is again like it's proportional to having the electron hole in the same spot. So the annihilation probability of positronium going into into photon is proportional to having them in the same spot. And the same applies to excitons. Yeah, that's unclear yet. There is no such thing as an individual exciton unless you play certain tricks like trapping them using Woodberg location, make sure that you just have one. I mean, there are experiments, right, like where you have a dipole shot with lots of, like in Valentine's group, right, for example, have lots of atoms, and you can also make sure that you just have one excitation. So similar ideas could also apply to excitons, where you just make sure through blockade, make sure that you just have one excitation that you can read out. Otherwise, there's no way of isolating this. Like there's no tweezer array of excitons.
First thing, the last lecture is from last itself is a below line. And then this 1 over R26, that R is like and then so there's below line all those kind of functions.
So if you, like in this naive picture, right, like if you have two excitations, but they're both delocalized, then you have then you can have the atom, one atom here and the other atom here. First, like you can have them in all sorts of different positions. And so quantum mechanically, like you just have a superposition of having the excitation in all sorts of different spots. or like if you have Woodberg. That's the nice thing about blockade writing. So it doesn't actually, like, as long as you're below the blockade radius, the phase that's picked up is the same for all pairs. Otherwise, you would get a mess, right? Like then they would all get like pick up a different phase depending on how far they're apart. Which does happen if you have an ensemble that is larger than the blockade bands.
So I had a question about some of the like some of the future outlooks you mentioned on this slide. Like when you say Woodberg exciton spectroscopy of semiconductors, like what exactly can we learn by study about semiconductors by like studying these Woodberg excitons?
So for example, I mean, this is what I meant with this example of the correlated states, the electronic states, in twisted bilayer system. So under certain doping conditions, you get very different fillings of the semiconductor with electrons. And so these fillings will have different field lines, basically, electric fields around them. And so this is something that you can detect because the exciton is very sensitive to electric fields. So then you would see the line shift, for example, depending on an electric field that gives you a star shift, or it would be deformed or something.
Semiconductors can be given superconducting character to doping. Like what? How do these two things make excitons and superconductivity, or do they not mix at all?
Okay, so there's actually like there's for excitons, like excitons are kind of like bound electron hole states. So I mean that's a like very interesting question. I think it has like multiple answers actually. So one is that you can somehow think about like exciting excitons on top of a superconducting state. So that is like something that is I think is very interesting. That's worth investigating, like an interesting direction. The other is that there's like at high densities, when you have lots of excitons, there's actually a connection between like an excitonic state and a BC state. So you can kind of go over from a BC of excitons to BCS state. That happens, as I say, like at very high densities. Does that answer the question?
Is